6.3 is graphing to solve systems of linear inequalities. So last year in grade 10, we studied systems of linear equations like we've looked at in the previous section with two different variables so that we were able to switch it into slope-intercept form, graph two separate ones, and the solution was the point where those two lines intersected each other or crossed. So the point of intersection was our solution. So let's do an example like that just to refresh our memories here. So solve the linear system by graphing. We have 2x minus y equals -1. We want to first change that into y equals mx plus b form so we know how to graph that. So -y equals minus 2x minus 1. So subtracting 2x on that side so that we can get y by itself. Dividing by -1, y equals 2x plus 1. And the other one, subtracting x to both sides. This one we have y equals -x minus 2. So graphing this first one, we have a y-intercept of 1 and a slope of 2 over 1. So y-intercept of 1, and my slope I'm going to go up 2 and over 1. And draw a line through there. And then this one, I have a negative slope of -1 over 1. So I'm going to go down 1 over 1, and my y-intercept is -2. Down 1 over 1. Down 1 over 1. Connecting those points. So last semester we would have said our solution is right here, this point of intersection, which is at -1 for x and -1 for y. That is our solution. Then to do a check, just to make sure, we plug those points back into one of those equations to see if it satisfies. So let's pick the second one, x plus y equals -2. Our x is -1, our y is -1, and that needs to equal -2. -1 plus -1 is -2, which equals -2. Therefore, we are correct. So this year, we're going to look at systems of linear inequalities like we talked about in 6.1, where the solution is going to be the region where the corresponding half planes intersect or overlap. So after we choose where we're shading on both of those lines, wherever both areas are shaded, where they have an overlapping, that's going to be our area for our solution. So let's do this first example. Graph the region defined by these inequalities. So we have x is greater than or equal to 0, y is greater than or equal to 1, and then we have 2x plus y is less than 4. So x is greater than or equal to 0. We want a solid line because it's greater than or equal to something, and that's going to be our vertical line. So this one will be blue. Here's where x is 0. This is x is greater than or equal to 0. And I'm going to, so before you shade, because you only want to shade where they overlap, I like to mark the areas I'm going to shade. So if I want greater than or equal to 0, I'm going to be shading this way. So I'm just going to remind myself, put little arrows. I want to shade on the right-hand side of that line when it comes time. My second one is y is greater than or equal to 1. So we find where y is 1, which is here. It's greater than or equal to, so a solid line. And greater than means I want to be shading above it. So little arrows to remind ourselves, let's shade above that line. And then let's do some work on this third one just to change the form. So subtracting 2x from both sides so we can have it into y equals mx plus b form. So y-intercept of 4. I'm going to go down 2 over 1. There's my line. I need to decide, am I going to have a solid line or a dotted line? And it'll be dotted because of our inequality does not have an equal sign. So a dotted line connecting those points. And it's saying y is less than. So I know that I want to be shading underneath of it. If y values are going to be less, I want to be underneath my graph. So what area is to the right of the blue line, above the green line, and underneath this red line? Well, that's going to be in this little triangle here, would be the shaded area that satisfies all of those three lines with their inequalities. And we can label that as the region of solutions. We'll talk about how to identify some solutions in a few examples, but this is the general area where I would have any possible solutions exist. So example 1, a sporting goods manufacturer makes footballs and soccer balls. Each football takes 3 minutes on a cutting machine and 1 minute on a stitching machine. A soccer ball takes 3 minutes on a cutting machine and 4 minutes on a stitching machine. What combination of balls can be made in 1 hour or less? So again, we want to start with identifying our variables and what they're going to be, so with our let statements. So let x be the number of soccer balls, how about? And let y be the number of footballs. We want to write inequalities to represent both the cutting minutes and our stitching minutes for both machines. So both the football and the soccer ball took 3 minutes for the stitching, or cutting, sorry. So cutting machine one first. Cutting minutes, we have 3x plus 3y, 3 minutes per football, plus 3 minutes per soccer ball. Has to be less than or equal to 1 hour or less is what we're told in the question. And if we're talking about the 3 is in terms of minutes, then we can't have less than or equal to 1 for 1 hour. We have to have that in terms of minutes, which would be 60. So less than or equal to 60. We can't exceed an hour. So changing this to get it into y equals mx plus b form, we need to subtract. I'll do that in another color so we can see our work. Subtracting 3x from both sides will leave us with 3y is less than or equal to 60 minus 3x. We want to divide everything by 3. So y is less than or equal to, changing the order, negative x. Negative 3 divided by negative 3 is negative x. 60 divided by 3 is 20, plus 20. So here's one of our inequalities we will graph. Now we want to do that exact same work for our stitching minutes. So in terms of stitching, our football needs 1 minute on the stitching machine, and our soccer balls need 4 minutes. So x is our soccer ball, so 4x plus 1y. And same thing, we're restricted to an hour, so less than or equal to 60 minutes. Subtracting 4x from both sides. We have y is less than or equal to negative 4x plus 60. Now let's graph both of those inequalities. So for my graph, I'm going to choose to go up for number of footballs here. For my y value, I'm going to go up by 5s for each tick. I'm just going to label 10. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, Let's add another tick on here to be 60. And then for our soccer balls, same thing. So 10, 20, 30, 40, 50, 60. So in our first equation, we have a y-intercept of 20 and a -1 slope. So I'm going to plot 20 as my y-intercept, and I'm going to go down 1 for our slope. But when our graph does not go down by ones, it's easier to find our intercepts and just play connect the dots, essentially. So we know our y-intercept is 20. We want to solve for our x-intercept. So what is my x when my y value is 0? So when y is 0, -x plus 20, well, let's add x to both sides. X also equals 20. So I know I have a y-intercept of 20 and an x-intercept of 20. My inequality has an equal sign, so I'm going to connect those 2 points. I'm going to try that again to be a little bit straighter for you. I'm going to connect those points with a solid line. I know that I want to be shading underneath because my y value is less than my x. So I'm going to again remind myself, shade this way when you have a chance. My next inequality is y is less than or equal to -4x plus 60. Do that in red. So I have a y-intercept of 60 up here. And I'm going down 4 over 1. For my slope, again, you can also just solve for your x-intercepts and to connect. So what is my x value when my y value is 0? So -4x plus 60. I can just add 4x to both sides and divide by 4. And x equals 15. So my x-intercept is 15. So I can plot that here and connect those 2 as best I can to be straight. Again, your straight edge is very important. I don't have one with my marker on the smartboard, so it's a lot easier for you to be neat in your work. Again, that inequality is less than, so I want to be shading underneath of my red line. So I need to figure out what areas would be shared if I shade under the red and under the blue. That's going to be this shape here. And again, if you're wondering, well, why are you only in this quadrant and not having all 4 quadrants showing? Because we're thinking our restrictions in terms of our questions. So we're talking about soccer balls and footballs. I can't have fractions. I can't make half a soccer ball. And I'm not going to have any negative ones. So I'm only going to be shading in this positive area. So some constraints or restrictions we can write to satisfy that is x has to be an element of whole numbers and y must be an element of whole numbers as well. So even though this question didn't ask us to actually solve, what it's saying is any combination possible with soccer balls and footballs has to be within that shaded region. So for example, if I picked a point, this could work. I could have 5 and 5. Any point that exists in there, if I have 5 soccer balls and 5 footballs, that would still satisfy the cutting minutes and stitching minutes so that I can complete that under an hour. If I were to pick a point, say 20 and 20 outside here, that's going to exceed my value of time. So I won't be able to finish that in 60 minutes. That's why it's not included in our feasible region, and our shaded region that we found overlapped both inequalities. So example 2, graph the solution set for the following system of inequalities. Choose 2 possible solutions from the set now. So now we'll find that shaded region that they share, and then we'll actually pick 2 points that could possibly work. Our first step is just to change each inequality into y equals mx plus b. So this first one, x plus 2y is less than 8. I'm going to subtract x from both sides. 2y is less than negative x plus 8, and divide everything by 2. Y is less than negative 1 over 2x plus 4. And our second inequality, 3x minus y is less than or equal to negative 6. I'm going to subtract 3x from both sides. I have negative y is less than or equal to negative 3x minus 6. I want to divide by negative 1, which means I need to switch my inequality. So y is now greater than or equal to 3x plus 6 is my second inequality. Now graphing both of those, the red one has a y-intercept of 4 and a slope of down 1 over 2. So a negative slope, y-intercept of 4, and from here I'll go down 1 over 2. Down 1 over 2, and there's my line. Identify whether or not I'll be dotted or solid. My inequality does not have an equal sign, so I'll have a dotted line connecting all those points. Its y is less than x, so I'm going to be shading underneath that line. So a reminder arrow, I want it to satisfy below this line. My green inequality, y-intercept of 6. And my slope is a positive slope, so 3 over 1. I'm going to go up 3 over 1. My inequality does have an equal sign, so this line would be solid. And its y is greater than 3, or y is greater than its x value, sorry, so I want to be shading above this green line. So which area on this graph satisfies both inequalities, both spaces that I want to be shading? That's going to be in this area right here, below the red but above the green. So this is my possible solution set. Any values that I think might satisfy both of these inequalities need to be picked from this area only. And that's what we're about to do next. We want to identify a few points. It can be any 2 points that you want that satisfy, and they are found in this area. So let's pick 2 points. Let's say negative 5 and 3, how about? Right here. That's negative, when my x is negative 5, 1, 2, 3, 4, 5, and y is 3. Yep, that works. So this is negative 5 and 3, and we want to test that point. That's in our shaded region. Let's see if that satisfies. So if I plug in, my y value is 3, must be less than negative 1/2 times 5 plus 4. 3 is 3 less than negative 5 over 2 plus 4 as a fraction over 2, which is really 8 over 2. So plus 8 over 2 is 3 less than 3 over 2, which didn't work, so I just caught my minus sign. This is a negative 5, sorry. So negative 5 times the negative 1 is a positive 5. 5 plus 8 is 13 over 2. So 3 is less than 13 over 2 is really 6.5 if you'd rather look at it as a decimal. And yes, 3 is less than 6.5. So sorry about my negative sign mistake there. Just catch that. It was a minus 5 and a positive 3. So this one satisfies. Does it satisfy our other one? Let's do a check. 3 needs to be greater than or equal to 3 times negative 5 plus 6. Is 3 greater than or equal to negative 15 plus 6, which is negative 9? Yes, 3 is greater than or equal to negative 9. So that point worked. The question asks us to choose 2 possible solutions. So again, any spot that you really see there, let's say right here, that is 1, 2, negative 3, and 1. It hasn't asked us to check, but it's always safe to do so. So we're going to plug those points in as well. So 1 needs to be less than -1/2 times -3 plus 4. So is 1 less than 3 over 2 plus, again, 8 over 2, our 4 is 8 over 2, is 1 less than 11 over 2, which is really 5.5. Yes, 1 is less than 5.5. And last check, 1 needs to be greater than or equal to 3 times -3 plus 6. Is 1 greater than or equal to -9 plus 6, which is -3? Yes, 1 is greater than or equal to -3. So identify your overlapped shaded region and pick any points if it asks you for any possible solutions. So those points just need to satisfy that shaded region and you need to pick them from there. Example 3. A sloop is a sailboat with 2 sails, a mainsail and a jib. When a sail is fully out or up, it is said to be out of 100%. When the winds are high, sailors often reef or pull in the sails to be less than their full capacity. Jim is sailing in winds of 22 knots, so he wants no more than 90% of the jib out. He wants to have at least twice as much jib as mainsail out. What possible combinations of mainsail and jib can Jim have out? So we want to try to come up with inequalities that would represent those situations. So first, verifying what our variables will be, identifying each. So let x be and let y be. So let's let x be the amount of jib sail out in terms of percent. And y can be the amount of mainsail. In percent. Some constraints or restrictions we're putting on this, well, we know we aren't going to have negative percents, right? We're only going to have percents between 0 and 100 even. So our restrictions in our domain or our range, our x, must be greater than 0 but less than 100, as well as our y. The question, however, says in this first one, no more than 90% for Jim. So explicitly from the question we know 90, but normally if we were looking at percent we would say 100. So our x one we can actually change to 90. X is less than or equal to 90. We know that one. So our first inequality is x has to be less than or equal to 90. And our second one, twice as much jib out as mainsail. So we need our x, which we said is our jib sail, needs to be twice as much as our y. In order to graph that, we want to make sure we have our y isolated by itself. So I would divide both sides by 2. Y is less than or equal to 1/2 x. And I didn't change my inequality, I just changed the order that I had this written out in. So, or otherwise I could have had 1/2 x is greater than or equal to y. But we're used to seeing our y come first, so I flipped the whole thing. Y is less than or equal to 1/2 x. And those are the two inequalities that we need to graph. So x is less than or equal to 90. Let's pick a scale of about, each of my x lines are going to go up by 10. So 10, 20, 40. Yes, that works perfect. 20, 40, 60, 80, 100. And I know on line 90, I need a solid line. X is less than or equal to 90. Solid vertical line representing my first inequality. I know I want less than or 90. So I'm going to remind myself I need to shade that way of my line. And my second line has a y-intercept of 0 because there is no b value there. So I know it's going to intersect at 0. And I have a slope of 1 over 2. So go up 1 over 2, 1 over 2, 1 over 2. And this line will also be solid. My inequality says y is less than, so I know I want to be shading underneath of my red line. So my overlapped area exists right here. So all possible combinations for this answer need to come out of that yellow shaded area. All possible combinations are in here. If we want to pick one again, just to check, let's say this point here, which is 60 and 10. So let's see if that point satisfies these inequalities. So for the first one, is 60 less than or equal to 90? Yes. Now here I enter both my x and y values because they have two variables. Is 10 less than or equal to 1/2 times 60? 10 is less than or equal to 30, which also satisfies. Your assignment is on page 317, number 4 AC, 6 to 10, and number 12. Once you're finished this, there will be a quiz on the first two sections of videos that I did with you. Please let me know when you have questions.